Okay, so let's continue with the lecture. Example 6.1.1. okay, so over there we mentioned about without Laplace smoothing. Okay, that's why I need to define what we mean by Laplace smoothing. Okay, so it's more or less similar by performing counting. Okay, as you can see in formulas 6.7. The only difference, we need to introduce something called alpha. Okay, some sort of smoothing parameter. Okay, as mentioned here. Okay, and then down here we need to also introduce extra alpha multiplied with m1, where m1 is number of categories associated with the feature xi. Okay, so with that we continue with an example from the internet explaining how to code it in R. Okay, since I've actually demonstrated in practical class, so I would basically just skip this. You can go ahead and try and run this thing. Okay, make sure you check the output. Okay, the output should be the same as the hand calculation over here. Okay, how we get this is more or less similar to example 6.1.1, which we mentioned just now. Okay, you can go and just perform counting. Okay, these are the outputs, right? Okay, so we skip this. Okay, and for multinomial naive Bayes, we will basically also skip it. I put it here because in practice, when you want to handle things related to text classification or spam processing, okay, this model is very important. Okay, there are a lot of YouTube explanations and also explanations on the internet, so I haven't got the time to actually include those examples, so I just leave it as it is, which is rather theoretical. Okay, hoping with Python implementation, maybe it's maybe easy for you to recognize some things like, okay, the probabilities here. Okay, you can find that it's actually using some log. Okay, you can see there are some log here. Okay, the calculation is just a normal probability. Okay, however, down here, as I mentioned in the formula, right, you can see the use of logarithmic function. Okay, so real-world calculation doesn't work like what we did previously, multiplying all the probabilities and that's the end of story. Okay, so that's not the case. Okay, we need to use log, and then we want the probability. We need then, after summing up all the log values, then only we take the exponential, okay, in order to get back it. Okay, every one of you would be able to see this, right? Okay, so this tells us that the formula I used earlier on, okay, actually gives us the probability. Okay, so then it's the naive Bayes for continuous data. Okay, so you can see here in the case of continuous input, right? Okay, then we'll be using, this is not exactly a correct formulation, but we will just use it for the sake of simplicity. Otherwise, we have to introduce different symbol for different cases. Okay, so in this case, we need to use probability density function instead of using the probability. Okay, because the probability for continuous values are basically 0. Okay, so we use the density. So, and as usual, we would always assume that the data are normally distributed, so that's why we have this normal distribution density function, probability density function. Okay, as for the estimation, okay, it's a bit similar with how we estimate the parameters for normal distribution functions. Okay, here's some Python code associated with Gaussian naive Bayes, right? Okay, so R can also handle it. Okay, and we will be proceeding to discussing example 6.3.2. Okay, despite the fact that answer is given, okay, there's some mistakes in my answer. Okay, so for part C, right, okay, correction is actually shown here. Okay, so we will stop because the video cannot be too long, right? Okay, YouTube won't accept it.